Hi, welcome back. Today's video, it will be some quite flashback on what we discussed so far. That's physics of standing waves. So I will just light and comment all such things which we have already did so far. What we discussed in the physics of waves. Generally, when we talk about the standing waves and strings, isn't? So I will just make the quite a snapshot of those things which we have learned so from the standing wave aspects. See, I will just try to visualize this all such in a very quite short time, and then after we will look for some problem sets in this context. But before, we will just make the once more the quite dealing about this. What the standing aspects in a given system means. For example, if we have the medium and we just disturb the given medium, but the medium it's very bigger in, isn't? So if the medium is very large, so we just disturb the given medium, and suppose that we get the disturbance after disturbing the medium like this. But when this sort of disturbance it happens in given medium, but medium is in principle very large, so what will happen here? This wave it will not move with the preferred wavelength. This wave there will be no any preferred wavelength because of the very large availability of the medium. Medium is very big in principle, so when we disturb such a medium, so what we feel there, the disturbance we got, it will not basically move with the preferred wavelength. But instead, if we have again a medium but with some boundaries, if some medium it's very short, means that we got the boundaries with respect to the given medium, and we just disturb the same medium, and thereafter we just get the disturbance like this. So in this perspective, it's very important to study such type of disturbance. Like what I mean to say here, suppose we have a medium but with boundaries. In a given medium with the boundaries, if we disturb such a medium, what will happen here? For example, if these represents the boundaries of a given medium, and we just disturb it, and we will get some disturbance, isn't? So when this disturbance it will reach here, it will reflect back. So for example, if this will reflect here, and in this perspective, when we get the structure of like this in a given disturbance, when we get the phenomena of like this, so the disturbance, the wavelength of a given disturbance looks to be a preferred, because this disturbance it will move with the preferred wavelength. Very interesting and very important here. What I mean to say here, so far, if we have a given medium and we disturb it, is it? And thereafter we just feel this sort of disturbance, and when this disturbance it hits then another end of medium, and it just travels back. So in this fashion, the disturbance we got or the wave we got, it will move with the preferred wavelength. Or we can say it will move with the preferred frequency. So in this context, it becomes very important to study the aspects of what we call as the standing waves. Standing waves. Is it very nice? So what I told here, suppose if we have the given medium with the boundaries and we just got the disturbance, but when this wave it travels and it will reflect back after hitting this boundary. So this is what I just preferentially mean, what so far mean from the boundaries of a given medium. So why it looks important for us when this disturbance it travels back. So this disturbance it will basically travels back this is also one of the possibilities. So in this way, what we call that this disturbance it must look that this disturbance it will move with the preferred wavelength, or we can say the preferred frequencies. This is what all about the standing waves is basically. So here actually it comes, it just clarifies this thing why it's very necessary for us to look about the aspects of the standing waves. And more about standing waves in the day-to-day lives, normally when we just play with some musical instruments, namely guitar or the piano, there are some strings which are being connected at both ends, and when we plug the wave, it's actually the phenomena of the standing waves that we probably see there. It's the different frequencies that we heard there through the different strings which are being connected at the both ends. It's basically the standing wave aspect, which is more or less familiar, that that helps us to understand everything where from the different musics come. It's basically the standing wave aspect. But still, we have the problem here. See, when we talk about the string, suppose it's a string, it's fixed at the two ends. The two ends of the string are being fixed. If I would pluck this string, so what I will get, as I told you before, I will just get the wave motion like this. Is it? And if the wave it will reflect back, we will get like this type of structure here. So basically, what we did in this type, suppose it's a string, have some length L, suppose, and we just fix it at the two ends. So these two ends actually represents the boundaries of the two medium. Sorry, boundaries of a given medium. That's a string having the length L. When we plug the string, we just got the disturbance. That's a transverse wave motion basically, and these two ends of a string are being fixed. What it means on us, actually the wave motion it nails down at the both ends of the string. Wave motion it nails down, and what the physicists call it, they call it's known as a node. Wave motion it basically nails down, or there is no wave at the both ends of string. So in this way we got the boundaries, a given medium with the boundaries. When we disturb the given medium, we just feel the standing wave aspects, and the string it will really vibrate through the different modes. But I told you there is a problem still. See how, let me try it here once more. If I will just consider here once more, there is a string, it's being fixed at the both ends, and when we just plug this string, the disturbance is being possible in it, and that disturbance travels like this. This is one of the way we can say. But suppose here, when this wave it reaches here, it may go with like this, this and this. This is one of the possibility. So if there is another wave that will go like this, this, this. So when it reflects back, this, and this is a very complicated type of superposition. Suppose a wave that travels in right plus the wave travels towards left, it's actually the resultant wave after the superimposition of two waves, namely left traveling and the right traveling waves is superimposed, and we got the idea of what we know as standing waves. But it looks quite not interested here, because if we study this sort of complicated superposition here, it will not provide us a better understanding. But instead, what we are going to do here, as I told you, when there is a standing wave in a given medium, actually we just look for the preferred wave or wavelength of the frequency of a given wave. And at the same time, when we look at this sort of a complicated superposition, we have the different wavelengths, and that's indeed looks a similar thing when we have the disturbance in a given medium. But medium is too large in principle, so disturbance in a given medium, we don't feel that there is a preferred wavelength. So what we are going to do still in this region, if there is a string, it's being fixed at the two ends. It's like the medium that has boundaries, and we just plug the disturbance, that disturbance propagates, it reflects, and what we got at the end, that's a standing wave motion. But still we got a problem here, that when we have this type of complicated superposition, what we are going to do, we just look for in which mode basically the string vibrates. Because if we look for this sort of complicated superposition, we don't get again this preferred wavelength here. What we are going to do in principle, we will just look for at what preferred wavelengths that the string will vibrate. That's nothing but modes of vibration of the string. It informs us about why it's basically important that we should look for in which mode the string will basically vibrate. The modes of vibration of a given string means that it's known to us, it acknowledges us through all the way around that the string, it may move with the preferred wavelength and all that, and it actually makes us to overcome that type of integracy here. If we just look for this complicated superposition, if there is a right traveling and the left traveling wave, they superimpose, and this is again the complicated type of superposition. It's not, very far from the, if there is a disturbance in a given medium that doesn't propagate with the preferred wavelength. Instead, what we are going to do here, look, We just make the use of concept that's a modes of vibration of a given string. In a given mode, actually the string it vibrates with a preferred wavelength. That's indeed a very important for us. Suppose if this is a string, it has a length L again here. It's being connected at the two ends. Two ends of a given string is fixed, and when we pull up this string, because the wave disturbance that will be set in this system, in this medium, so this is one of the possibility that this string it may vibrate with this type of wavelength. This is actually the big daddy here, isn't it? So it may vibrate like this, it may vibrate like this way. So this is one of the possibility, because if we are going to make this description of this thing here, it provides us this kind of understanding that the wave it basically disturbs it, actually it travels with our string vibrates with some preferred wavelength. So this is nothing but the wavelength we got from the last discussion, that wavelength it's related to the modus of vibration, and by means of this relation, when n is 1, lambda is basically 2l, l is lambda over 2. If I will just make this wavelength full, this is basically nothing but the first half of the wavelength. So the string it will vibrate of the order of the half of the wavelength of a given disturbance that will propagate here. But what it actually confers of the string it will vibrate, or the disturbance we got between the two ends of a given medium, it vibrates or it moves with some preferred wavelength. That's actually the key intuition while on describing some different modes of vibration and all that, and what's the corresponding frequencies of vibration. We got that type of relation also. That's frequency of nth mode of vibration, that's n times the frequency of first mode of vibration. This is a fundamental mode, or we can say it's a fundamental frequency. The wavelength we got, the corresponding frequency of this type of wavelength, that's known as a fundamental frequency or the fundamental node. So because we got some sound after playing some musical instruments, we just feel there is a sound. There are the different types of musics. That's as a consequence of this standing wave motion, basically. So anyway, it's actually these two relations. It actually confirms us that in which mode the string it will basically vibrate, and what kind of preferred wavelengths we got from this kind of discussion. That's why we just make the use of concept that why it looks essential for us to study the aspects that in which mode basically the string it will vibrate. So anyway, I will just look for two problems that I fixed so from this discussion. They are very simple, but it needs some efforts that we have to do anyway. Here, let me say, for example, if there's a problem like as the string it vibrates in the second overtune. If the string that vibrates in second overtune, if the string vibrates in second overtune, what are the number of antinodes and nodes between the two ends of the string? See, it's very important to mention the boundaries of a given medium whenever we talk about the standing waves. You may ask me a question why the discussion I made so far, it's the enough explanation of this fact why it's important. So strings actually it vibrates in second overtune. We need to calculate here what are the nodes and number of nodes and antinodes between the two ends of a given string. Means we don't have to take into account the nodes or antinodes at the ends of string. It's known to us that the wave motion it basically nails down, and the fancy term of this context is known as node. Node is basically where there is no motion, where there is no wave. We just call it known as node. And there are some another type of regions, we just call them antinodes. Antinodes are basically such a region of a given wave. It means the motion is maximum, is it? So it will be confirmed from this type of problem. make the visualization of this bit here. So when we plug the oscillation in it, but question actually tells us about what should be the, I mean, number of nodes or antinodes between the two ends of a string. When string, it vibrates basically under the second octave. Is it? So second overtune means the third harmonic. Second overtune means third harmonic. When string, it vibrates under the third harmonic. So how we can figure out here exactly the nodes or number of antinodes between the two ends of a given string. We need to be, remind here the relation we got. So actually this L is, suppose this is the length of a string. For third harmonic, N is basically 3. So lambda is just 2L by 3. Or we can say, yes, L is 3 half of lambda. If there is some preferred wavelength, and basically under third harmonic, string vibrates 3 half of lambda. As we know, whenever we talk about the wave, so from here to there, what we got, it's known as lambda. Isn't so? From here to there, we have lambda. But from here to there, for example, string is long enough like this. Okay. From here to there, we have lambda, and there is a pending half of lambda. When we have lambda plus lambda half, what we got here is, it's 1 plus 1 over 2, that's 3 by 2 of lambda. This is a way by which we can draw this waveform here. And anyway, this actually represents the third harmonic of a given string that vibrates here. So what we need to find here, yes, but when the string it's being fixed at the two ends, we expect there is standing wave motion. So by this way, we can calculate actually the nodes are the number of antinodes between the two ends of string. We don't have to be include the nodes at the two ends. We have to be exclude the nodes here. Actually, we have to be exclude the number of nodes which are going to be held between the two ends. So see, we should look for what are the possible number of modes after excluding the nodes at the two ends. It's known to us when the string it's being fixed, so wave motion it basically nails down at the boundary. There is no wave motion at the boundaries. So we specifically say that actually it's a node. It's node. So, but we have to be exclude these two nodes. Whatever the number of nodes are being to be in this type of third harmonics, we have to be, look for those. So this is a one node, this is second node. There are two nodes. There are two nodes, isn't it? But in context, here the displacement is maximum. It represents actually the motion is maximum. So that's what the physicists call it antinodes. So there are how many nodes between the ends of string? That's 2, but there are 3 antinodes. 3 antinodes and the 2 nodes are being found when the string it vibrates under third harmonic. This was actually the exact content from the question which we are generally asked to find. So from this actually it problem ends here. So what we can confirm from this, when the string it basically vibrates, it vibrates under the third harmonic or second overtune. That's actually the conditional that we need to be imposed from the given question. But what we got here, the string it basically it will vibrate under 2 nodes and 3 antinodes. Anyway, if I will just look for another problem here, that's again in context with the standing wave motion aspects. Suppose if we have the displacement solution of the two traveling waves, one travels along right and another travels along left on a string. If we have the displacements given from the question of the two strings, yes, that's A some sine of kx plus omega t, and y2 it's also given a sine of kx minus omega t. These are the two possible displacement solutions which are being traveled, displacement of the given sine waves which are being traveled along the string, which are being traveled on the string. So we need to find here, yes, what's the adjacent distance between the two antinodes. What is adjacent distance between two antinodes? But if we look at the formal displacement solutions of the two waves which are being traveling, say here from here. So if I will write this first, this second, it will not affect our result. So after doing this all such, because it will show the superposition phenomena, because this wave it's basically traveling along this way. So if I will write here omega t first, this kx at here, again omega t, this yes, omega t here, and minus kx here. If I look for the first displacement solution of a given wave, which is basically traveling in a string on a string towards right, this is a right traveling wave. But if I look for the displacement of the second, see, a is here constant, in with which speed the wave moves, that's again constant. K is here the propagation number, that's again constant, means the wavelength of a given wave, it's also constant, and K is known as the wave number of the propagation number, it's related to the wavelength, is it? Because here is K, here is K, here is amplitude of the two waves are same, the speeds of the two waves are same, as we know that omega V, it's basically omega R. Under a more general representation, V is omega cross R. So here is omega, here is omega. We have again the same, waves are going to move with the same speeds, they take same time, and they have the same wavelengths, but only difference is there. The two waves basically, one is the right moving wave, another is the left moving wave. And when the superposition is possible, what we will get here the standing wave. Is it? I don't need here to draw a figure and to perform this all side. This is when I discuss the first class of this standing wave motion, what it exactly means, where we describe this all such there. But I will just look at what's the content of question. Question basically tells us to calculate exactly, yes, question basically tells us to find what's an adjacent distance between the two, what's the distance between the two adjacent antinodes. So have a look here, how we can do here, very simple. See, if we will just write down the superposition of the two displacement of the two waves, because when they superimpose, we will get the standing wave, and then only then we can calculate where are the antinodes are being, what's the number of antinodes and what's the distance between the two antinodes. That's all only being confirmed after this superposition, is it? So if I will just remind as it's a sine, yes, omega t minus kx plus sine omega t minus kx. These are the two displacement of the two waves are given. One is a right traveling, another is a left traveling, with the common characteristics like a, omega, k. These are some common characteristics, and which are indeed the necessities of the two traveling waves along the different directions, opposite directions, relative to one another. So in this context, we will basically get the standing wave. But how we will carry on the what's the condition from the given question that wants us to find? Basically, we need to calculate, yes, what's the what's the distance between two adjacent antinodes. After solving this all side, what we will get here is A, it will be cos omega t sine kx, because we did it in a first very discussion regarding the standing waves. So from that we can convert this thing, because it's a CD formula. After doing this all such, we will come to reach this type of, this will be the 2 here. So what's basically the amplitude of a given wave is 2a sine kx. I can put it the modulus here. It represents actually the amplitude of a given wave. When there is a maximum displacement, generally what we call, yes, when wave basically propagates on a string, where we show the phenomena, we show the observation like this. Generally when we talk about the standing waves, and this actually represents the maximum displacement, that's known as an amplitude. And when we look for an amplitude, it represents the point that's known as antinode. Antinode means the maximum motion, is it? So anyway, it's actually the confirmable that what we need to be what we have to be calculated from the given condition of question, that we have to find what's the distance between the two, and what's the distance between two adjacent. This antinode, it's adjacent to this, and we can say this antinode, it's adjacent to this. That's why I use here the modulus, so it will not made us a problem regarding this calculation. Anyway, so how we can do this all such? We know that this represents actually the amplitude. Amplitude will be maximum when the sign of this argument will be maximum. So when the sign of this argument will be maximum, yes, when sign of this argument will be maximum, if I write here sine kx, it must be n plus half of pi, where n is 0, 1, 2, 3. If we assert this sort of numbering to n, we will always get some half integer multiples of pi, or that values of pi. Sign of this argument is always maximum. That's indeed the maximum that we need to take here. It's because we should look for what's the distance between two adjacent antinodes. And when there are the adjacent antinodes, when there is an antinode, means that it's actually the maximum displacement. Anyway, we got idea from here right now. So sorry, it must be here sine kx must be sine of this value, because it should be maximum. It should be maximum. Anyway, if we put n as 0, it's sine pi by 2, that's 1, that's maximum. So by that intuition, it will get always the maximum values after asserting this numbering to this n here. So anyway, we got here what we need to find. Yes, sine, it will cancel. So kx, we will get, yes, it's n plus half of pi. So kx, it will be, yes, when n is 0, 1, 2, 3, and so on. When n is 0, we will get here, yes, 2 by pi, pi by 2, is it? And when n is 1, we will get here 3 pi by 2. When n is 2, we will get here 5 pi by 2, and so on. These are the possible values of this sign of this argument, over which we will get, wherever the antinodes are being located in a given standing wave of where the two traveling waves are given. So it's all actually we done according to the given data. So here, by this way, what we need to find here x, actually the distance between the two adjacent antinodes. See, this is actually kx, it's pi by 2 here, from here to there, and kx, it will be 3 pi by 2 from here to there. But we need to find the distance between two adjacent antinodes, means whatever distance from here to there and whatever distance from here to there, it's pi by 2. So if we will just subtract this from this, we will get exactly how the any two adjacent antinodes are separated from one another. That's pi by 2, isn't it? That's basically pi by 2, or simply pi. Sorry, this is 3 pi by 2 from here to there, and this is pi by 2. So pi by 2, it will be 3 minus 1. It will go with this. So we will get the pi here. So kx, it's basically the distance between two adjacent antinodes. That's pi. So x will be equal to, yes, pi by k. This is the answer to the question. That what's the distance between the two adjacent antinodes if the two formal solutions of given displacement waves are given, which are going to be along the two ends of a system moving opposite relative to one another with some common characteristics. Like that's what the requirements of the standing waves are. By this intuition, we got the idea how we can carry out all such data, and we can find out, I mean, after using the conditionals from the given problem, and how we can find out this demand, that how the two adjacent antinodes are being separated from one another in a given standing wave motion. So I just picked the two problems. This was all about the standing waves, is it? So thank you.